Welcome. So I'm going to kick off this week actually going back to something I saw in some of the discussion boards the last couple of weeks. There was a few people who were saying things like the alphabet doesn't really work. And in truth, if we only leave it to 26 letters, there's a lot of other reasons. But we always are changing things into numbers. In fact, we don't really do cryptography on the symbols themselves. We're always doing some kind of way of transitioning from our symbols to a number. And there's multiple different ways to do that. And it's all based on actually what are called base systems. So I want to talk about this just briefly. So we'll talk about the bases of bases. I'm not trying to be punny here. I'll move on to base 26 specifically, and I'll end with talking a little bit about ASCII, which actually can be done in multiple different bases and the different bases I've seen in it. So let's just talk about base 10. So base 10 is the base system that you've done. And I'm actually gonna do this more freehand than actually just have a bunch of specific recorded values. So to help you understand, back in elementary school, if I gave you 328, what does this number mean? Well, you know that this number is the hundreds. So this is 3 times 100 plus the 2 is the tens, and the eights are the ones times 1. But 100 is the same thing as writing 10 squared. 10 is really the same thing as writing 10 to the first power, and 1 is 10 to the 0 power. So the truth is you have this. So this place right here is 10 to the 0 powers. This is 10 to the first powers. This is 10 to the second powers. The next one to spot would be 10 to the third powers. The next one after that would be 10 to the fourth powers, and so forth. This is actually how scientific notation really works. We don't usually teach it this way, but that's actually based on our number system. Further, when you were learning things in elementary school, if I did that 328 again, and I did it times 10. So if I multiplied by 10, you were like, that's super easy. It's 328 with an extra 0. Why is that? It's because each of these tens suddenly just went up in a power, which means they shifted the spot they are. So in base 10, all of our numbers, the rightmost number is 10 to the 0 power. The next one is 10 to the first power, and so forth, and so on. Like this, 10 to the third, just like I've already kind of explained. So this is the idea. You've actually been doing base 10 the whole time. Now, the funny part is if we actually taught our base system and explained what we were doing at an earlier age, I think it would make more sense. But they never seem to teach it this way. They just tell people to do it. They don't explain to them. They maybe do this, and actually I see them now doing a bunch of visuals in elementary school where they break them into like ones blocks and tens blocks and so forth, and not understanding that's a base system that we're based on. Now, we do actually use other base systems besides base 10. If you ever check, we use a base 12 calendar system because our numbers are based on this idea. In fact, they're modular 12, but the idea still exists. But if you look at calendars, have you heard the Mayan calendar ended? It's because you're using a base 12 system and it ended up a certain way. Another base, though, that's common in computer science, there's a couple bases that are very common. The most common is probably binary, and we've already discussed this a little bit, but binary is just base 2. So base 2, if I gave you the number 1011013, I can't do 3 because every number has to be essentially modular 2. So I'd have to do 1 1. Let's do 1 1 1. What's this mean? Well, this first spot, again, this is 2 to the 0 power. This is 2 to the first. This spot is 2 to the second, and so forth. So if I broke this out, so let's count our spots. So this is 0, 1, 2, 3, 4, 5, 6, 7. So that first number is 1 times 2 to the 7th power. And then I can skip this, but I could write it, if I'm writing it out, it's 0 times 2 to the 6th power, that we all know that's going to be 0, plus 1 times 2 to the 5th power plus 1 times 2 to the 4th power plus 0 times 2 to the 3rd plus and so forth and so on. And then we just have to calculate all these values, which would be 128 plus 0 plus 2 to the 5th is 32 plus 16 plus skip the one that's for 8. And then I have a 4 plus a 2 plus a 1. And now I just need to add these together. Interesting enough, you add these two numbers together. These two together are going to give you 160. These two add together give me 20. And this gives me 3. So add it all together and we get 183. So this number right here in base 2, often we do base 2 by doing a little 2 subscript, is equal to 183 in our base 10 number system that we're accustomed to. So binary is probably the primary one that a lot of computers do because they love using bits. By the way, quick note on that. Any of you who are old enough to actually remember anything or go Googling, I remember when I was a kid that we had a 32-bit. Nintendo came out with a 32-bit system, and then a 64-bit system, and then one 28-bit system, and then a 256. And if you also go back and look at the size of, I mean, long time ago, how many megabytes? They again were all in base 2 because in reality they're just saying how many bits are in there, and bits are binary is often how we store them. Now, another system that's very common in computer science is what is called hexadecimal. Now, hexadecimal is base 16. Now, wait, so the problem is now we actually need 16 different symbols. We obviously have the numbers, the digits 0, 1, up to 9. That is 10. But how do I deal with my other 6 digits? Well, all we do is we just do A. A literally represents if there are 10 of something. B is representative of the number 11. C, D, I'm going off the screen, so I'm just going to keep coming down to E and F. So F is actually 15. So I could have something that's like 3, 5, 8, A, 9, B, F. That's supposed to be an F. I don't know why my brain said F. My hand wrote 5. Let's go an F right there. So we have this thing, but again, it's the exact same situation. So we can just count how many spots. This would be the 16 to the 0, 16 to the first, 16 to the second, third, fourth, fifth, sixth. So this right here is really 3 times 16 to the 6th power. And then we're going to have 5 times 16 to the 5th power. If I want to convert this back to base 10, plus 8 times 16 to the 4th power, plus, and then now let's get A. Well, we can't write A times 16 to the 3rd power. That doesn't make sense in terms of base 10 because A doesn't exist in base 10. So instead, we'll replace the A with a 10. And again, we'd have 9 times 16 squared plus B, which is 11 times 16 plus F, which is just 15. So this is the idea. And then we just have to do the calculations and all these things raising to a power and going from there. That's actually how we get from hexadecimal to base 10. One question comes, well, how do we go back the other way? So what if I gave you the number 100 and let's say 3, and I want to know what this is base 10. Well, I'm literally going to have, I mean base 16. So this is in base 10. The question is, what is this in base 16? And sometimes it's written this way in some number theory books and other things like that. Well, the way you have to do that is you literally have to look at the powers of 16. which would be 16. And then 16 squared, for any of you that are aware, is 256. I could do 16 to the third power and so forth, but 256 is bigger than 103. So this is 16 squared. So I actually know that 103 can be written as something times 16 to the first power plus something times 16 to the zero power. And so because this number is bigger, I'm going to need 2 digits to write this in base 16. So we start off and we say, what is 103 if I divide that by 16? And 103 divided by 16 is going to give you 6. So 103 equals 6 times 16, but with what remainder? And so this is where we get back to that whole quotient thing. And we're just going to utilize this one more time. And that's actually going to be a remainder of 7. So this actually would be 6, 7. We'd write as 67. We actually don't say 67. That's where we have to say 67 base 16. So because 60, it's not really 6t. 60 is 6 times 10 to the power. This is actually 6 16s plus 7 more. So that is actually how this idea plays out. And so you have to figure out what are the powers of my thing and break it down and so forth. So we do this all the time. Now, one base that we're going to use a lot in this class, in fact, we've already done it, is base 16. So to understand this, let me just do a very simple example of base 16. I mean, base 26. So base 26, I could hypothetically, I could change this number. I could start in base 26. I could have the numbers 0 through 9, and then have letters all the way up to essentially 25. But another way to do it is just like we've already done, where A is 0, B is 1, and so forth, and Z is 25. And if I do that, then cat, the C is simply a 2, A is 0, and T is 19. And I'm putting commas because this is again going to be times 26 to the second power. This is the 26 to the first powers, and this is the number of 26 to the zero powers. So this is 2 times 26 squared plus 0 times 26 to the first power. I know that's absolutely going to be 0, but again, I'm writing it down just to help illustrate the idea, plus 19 times 16 to the 0 power, 26 to the 0 power, but that's this is just 1. So if I multiply all this out, and I'm not going to go through all the simple little steps, but this is going to be 1371. So base 26, I could take the word cat and instead make it this. The problem with this is that we have to be consistent about how long our string is. So in other words, how long are my base 26 quote unquote words? Words are simply symbols connected together. So while you see the word cat from the English language, I see the symbols CAT and what those make up quote unquote a word. So let me do a much more complex one. What if I gave you the phrase, the cat is black? Now, the way that we often do this in cryptography is actually we come up with very common length terms. So in other words, notice I got rid of all the spaces, and I know that looks really, really cluttered. So in fact, I could clean this up just a little bit, and come back here and black this. So often, and actually the common length is 4 or 5. So let's do it in groups of 4. That's what I did for this particular example. And then we're again going to do groups of 4, and then we'll do groups of 4. And notice it's going to leave this K. What do I do here? And I'll talk about that in just a minute. If I translate these directly into numbers, again, using the 0, A is 0, B is 1, C is 2, etc., this gives me the number essentially a list of numbers that's going to be 19, 7, 4, 2. That's what THEC is going to turn into. I'm going to do a break, and then my next one would be 0, 19, 8, 18. Break. BLAC would be 1, 11, 0, 2, and K is just 10. Now notice I don't have anything hanging on here. So one of the tricks we often do in cryptography, and I'll again reiterate this again later, is we give dummy letters. So we actually just pick letters that are all the same. So in this case, I need 3 more letters. So I'm going to pick the letters Z, 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 because what on earth is that? That's not going to make any sense. So when I retranslate it back, if I was decrypting this back into letters, I'd be like, oh, these don't make sense. I'm just going to drop them out because these are very rare. Again, you can throw in Qs and other things like that. So that would be the numbers 25, 25, and 25. Again, if I simply took this right here and turned it into, this would be 19 times 26 to the third power plus 7 times 26 to the second power plus 4 times 26 plus 2, that turns out to give me 338,782. Okay, so this block I just turned into, and actually what we often do to make it even more clear is, believe it or not, is actually get rid of the commas. Because then there's not, comma is a break where we're doing a list, but it's also a break that we sometimes do for things, but that's not actually a common thing in your computer. That's why a lot of computers will actually return numbers without commas because they don't want you to infer that there was a break when really it's just trying to read the number better. If you're displaying it for someone else, numbers are always nicer. I mean, have commas. Helps people recognize. Our second block, so that would be the first block. Oops, I was sorry about that. Our next block would actually turn out to be 13070. Our next block would be 25014, and the last block with all those Z's is actually 193,335. So in this situation, we have a lot of different numbers. So here's an interesting question, and this is part of the question I want you to think about for the discussion board. We'll keep on going on. I'll type it on the discussion board, is this. Given this example of the cat is black, if I was to do some kind of algorithm where I take my message and I'm going to work on it mod P. I'm going to do some kind of algorithm on it mod P. I don't know what the algorithm is. We'll take F of that. My question is, how big or how small, how big does P have to be? Or in other words, what's the smallest P value that we could use? What are the bounds or limits on P? Looking at this example, I want you to think about that for a second because that is one of the critical concepts here. Is we have to understand if I did 4-letter blocks versus 5-letter blocks, and whichever one I choose, and 4 and 5, by the way, are the most common groupings. There's also 10-letter blocks occasionally. And I've even seen where they just do all the letters all together, depending on if it's a short message. But usually there's a known amount that we're doing this into blocks, and then we're just scrambling that up. And when you decode this, it's kind of unscrambles it and so forth. So that's your question. What's the minimum P possible for this particular example? All right. Let me talk about one other key detail, though, I think is good to talk about. What are some pros and cons of the base 26 system? So let me just give you a couple of pros. I mean, obviously, I already have letters. I just translate them quickly over, and I utilize this. But one of the shortcomings or cons of this is if I do base 26, I have 26 symbols. That means I can only do, for instance, a capital A. I can't do lowercase or capital. I just does A. So case-wise, we lose cases. I also don't have numbers. I can't include numbers in the grouping because all the letters are taking up all the spots. What about any other symbol I want to send? Can't do that. So suddenly we actually have a problem here with a base 26 that it doesn't actually include enough spaces for us to deal with it. And we can still expand that. So even if I just did, for instance, the number of numbers, this goes back to your discrete math times. There are 26 different letters. So we have 26 lowercase letters. We have 26 uppercase letters. We have 9 digits. These are my digits. That alone, just for each spot, I could hypothetically, that's without any other symbols, that is 61 different symbols I'd need. So I could do a base 61 and so forth. It turns out that a few years ago, we created a different system that is commonly used, and it's called ASCII. So you'll notice in many of the problems I'm starting to give you, I'm already telling you the message has been encrypted in M. Here's the message. And I'm asking you simply to translate the message. I'm not telling you what the original message was in terms of letters. I'm just telling you what it is in terms of a numerical value, because it depends on what ASCII if we're using ASCII, if we have our own built-in system, there's a lot of different conditions. But let's talk about ASCII for a quick second. I hinted at using bit strings earlier, and actually that's the key thing. So ASCII uses an 8-bit strategy. That means that each letter, number, symbol is represented by 8-digit or 8 binary thing. So for instance, here's a few examples. A, the lowercase a, is literally all zeros. Lowercase b, all ones. This starts to feel. The uppercase a, look at this. Can anyone guess what in ASCII, if I gave you the value 000110000, what would that be? And you're probably like, I don't know. Well, if you think about this spot, let's just look at this. This is 2 to the 4th power plus 2 to the 3rd power. Well, 2 to the 4th power. So this is 2 to the 4th power. No, that should be an exponent. My apologies. It's 2 to the 4th power and this is 2 to the 3rd power. Well, this is going to be 16 plus 8, which is 24. Look familiar to anybody? And you might be like, it seems like, why didn't they just do 26? It's actually because we kind of ignored the letters that are not common and made them other places. The space value you can see here right on the end of the screen is actually, it's very simple. So you can literally have spaces down in my message and I can turn it into this. This is a bit system. It's 8-bit. So you have up to 8 different spots to account for. Again, going back to your discrete math days, that means you have 2 to the 8th power, or in other words, 256 possible symbols I can use. Excuse me. And these symbols are actually the idea that we are going to leverage with ASCII. Specifically, we then take it a fixed length B. We can actually make it longer than 8 bits. We can make it 20 bits. We can figure out however long I want to do it. So you gave me a plain text message, and I make it a bit strings of whatever length that is. And so there's exactly B of them, and they're all zeros and ones. And that's called my block size of my cipher. So I can actually create this plain text, and I could have it where I'm just gluing them together. I can have it where there's some kind of, this word is represented by this bit in this size and other things like that. By the way, ASCII, you can go look it up. You can see ASCII in base 10. This is obviously in bits, so it's an in base 2 format currently. It also can be done in hexadecimal form. Lots of different options depending on how you're programming and so forth. I've actually seen a lot of hexadecimal stuff when calling specific symbols out for Java. So this is another thing. So in general, we create a list of a message, and we encrypt it, it takes each block and it creates a ciphertext block. But in order for this to really work, we have to kind of have the same number of values in each block. That's where I came out. Remember last time I put a bunch of Z's? I could also throw in a bunch of zeros, or in other words, a bunch of A's, if you're thinking about it that way, on the end of the block. The other problem with this is ASCII. If I'm using ASCII, or even if I come back here to this system that we talked about here in this example here, I have to have that known. So if I'm doing public transmissions, the strategy I use to take this and turn it into a number has to be openly known. I have to tell that publicly what I did, because the only math, the only trick is not how we took this and we turned it into a number. This word, this phrase, this whatever message I want to send, it's not how I turn that into a number. The math is all about taking that number and changing it to a different number. And the process going from the first number to the second number makes it almost impossible for other people to know if they don't have all the information. And that's what we're going to get to as we continue on talking about public encryption. All right, so good luck. Let me know what questions you have.